Hello and welcome back to ST118 Statistics and Applications, Session 6. In this video, we'll discuss probabilities. Now, probabilities are very important in everyday life and business situations because we use that to make decisions. All right. And what exactly is probability from the theoretical point of view? So that's something we like to discuss and cover. And from that, it naturally extends to what you might have heard of as conditional probability. What is conditional probability? How do we use it? And the notion of independence, something that a lot of statistics and probability theories and tools rely on, right? Kind of like part of the assumption. So we need to have a more concrete understanding of this important assumption. Then we look at a very, very useful and powerful, almost magical tool called Bayes' theorem, right? And its applications. All right, let's get started. So for probability, what is probability? I like to propose a concrete way of looking at it. Concrete means you can point at it, you can look at it, you can tell your friends and say, see, this is it, right? And that is basically counting, right? Counting. Now, there are two, before I write down the counting method, there are generally two camps, two schools of thoughts, even in the statistical world, right? The professors and the experts cannot agree, and they still have two world views, two perspectives about probability. You and I know that probability is very nebulous, very fuzzy, very untouchable, very invisible. And yet we all feel the effect of probabilities, right? That if you look at the sky and it's cloudy and it's dark, you say the chance of raining in the next hour or before end of the day will be very high, and you probably throw a number at it, right? Your high could be 80%, someone else's high can be 95%, right? So you just throw a number at it. This kind of thinking, right? It's kind of like a personal probability, right? You just throw a number based on your feel and events is the Bayesian idea, right? The Bayesian, yes, the same Bayes theorem here, right? And the Bayesian theorem, Bayesian view of probabilities is just very based on subjective feel and understanding of the reality, right? Right. So reality is reality, but how you feel, how you think, might be different for different people, and so that kind of allows this strange behavior that if you ask your friend, what do you think? It's cloudy, dark sky now, right? What do you think of the probability of raining? Before end of the day, that friend of yours might say 75%, and you might say, no, I think it's 90. How come there is a difference, right? So this view, this Bayesian view allows us to accept, right, these somewhat inconsistent, but they are all high probabilities, but they are not the same number, right? And because they are subjective. And so when we further look at the sky and there is thunder, there is lightning, but not yet raining, then these are further evidence to say, oh, now I want to revise my probability. I think the chance of raining is going to be 95 and then 97, 99%, right? Yeah. So you, because of more evidence, you update your probability. So that's the Bayesian kind of thought. You don't have to measure infinite number of times. You don't have to have 100 times of rainy days, then you can count and calculate probabilities. As opposed to, yeah, that's right, the other camp, the frequentist way of looking at things, which is to count, right? Which is to say that, you know, in the past month, whenever I see the dark clouds, right, uh, of the 20 times I saw dark clouds, 18 times resulted in rain before end of the day. So therefore, the chance of raining is 18 over 20, right? So that's the view. That's the counting view. And it is going to be that view that we are going to talk about, right? So the probability of an event A, right, is going to be defined as the count of A. So I'm just having this C function here. C function here is to basically say the act of counting, right? So in Excel, it may be summing, right? In R Python, you just sum up the numbers that qualify to be part of the A set. So, so for example, A might be here, right? And you can have a universal set that is surrounding A. So that's our universal set. Right? So if we go by number, we can write a number there, right? So we can say that set A here has got 5 units, some whatever is qualifying to be part of A, for example, right? 5 can be people with flu, right? And the household, the extended household family might have 15 people, or yeah. So A will be 5, and those non-A but part of U will be 15, right? So the probability of A here in this case is going to be count of A, that's 5, count of U, that's 5 plus 15, 20, right? So cancel off, you get 0.25. So that's the frequentist view, and it is this view that is very useful for us to do data analytics, because that exactly is what is happening, right? We collected a lot of data, gigabytes, maybe even terabytes of data, and we like to extract insight from those data, and by counting, right, which events or how many times did those measured data meet our interested area. Interested area could be that the data is very large, very high. Yeah, so the number of items purchased, for example, very high number of purchase customers, how many are there versus how many customers we have. That will be probability of going forward. That will be the probability of a customer when the customer buying high number of items from our e-commerce store. Right? So high, again, you decide. Maybe it's 10, maybe it's 20. So okay, so that is a very simple idea, and that's essentially as simple as it goes. The counting, yes, we do need some kind of discrete items to count, if I put it this way, right? Count. But if it is going to be sand-like, that means the items are so numerous, like data analytics, right? So numerous, so small, so numerous, but non-zero, right? So in there, we might just approximate it. In fact, not approximating, we're using exactly the area to become the count. So if the area is large, then it's like representing larger counts, and the area for the universal set will be the number of items in the universal set. So it can extend to summation, right? Because if we have a lot, we don't go one by one, 1 plus 1 plus 1. We don't go that anymore. We do go by summation. If it is even much more numerous, like area-like or volume-like, then we go by integration. So you do find integral signs a lot in probability, right? And you have when you look at probability distributions, then you will in fact see a lot more of these very sometimes complex distributions, functions to describe those areas. Okay, but we're not getting into that. We want to talk about the idea of probability that is useful for us to make decisions. So from here, counting over counting, right? So we can have probability of A, probability of B, and that will be just C of A over U, C of U, C of B over C of U, and so on and so forth. But of course, we can also have conditional probabilities, right? So conditional probabilities would be two given events. So we would have to have another event, sometimes a subset of A, that's fine, but I'm just going to use two events, right? Even if it's a subset of A, then we'll have one subset of A and another subset of A being two smaller events. So why divide something into smaller and smaller pieces when I can certainly carve out another segment here, right? So if I were to call B to have something, right, then clearly A cannot be fully having 5 here and nothing in common. So there's something in common, right? Something in common here, let's call it 2. And so A will have to have a net count of 3. I will not erase the 5 because it's meaningful here, right? It was meaningful then. But now I have a B, so I put 2 units here that is in common with B, and 3 units are not. They are purely A. Okay, and for B, I will have another, let's say, 4 units here. So B has 6 units altogether, right? These are in mutually exclusive areas and counts. So B has in total 4 plus 2, 6 items, right? Sometimes the maybe textbook or some literature, they will represent B as totality 6 with some overlapping area, and then they will write 2. But it's confusing to see 6 and 2. Is 2 part of the 6, or should we add 6 to 2 to give the total for B, right? So I'm just going to write out the mutually exclusive counts. And of course, we have to update the 15 because U, the universal set, we meant it to be 20 units, but now I've introduced 4 units into B, 7, 8, 9, so I better update this to 11. Now, this is not Bayesian update. We're just recarving out, redesigning the U here. Okay, and so what's going on? So let's just practice a little bit more. We say that the P of B is equal to count of B over count of U, and that is going to give us 6 over 20, right? 6 over 20, and we can leave it as that. Yeah, and now we want to define conditional probability, right? So let's define conditional probability. Define conditional probability of A given B, right? So that's given B. The vertical bar is pronounced as given B. Given B is, first of all, the probability of A and B happening. So this is and intersection or and, right? So that means this is the intersection, A and B happening, right? So the intersection, the and, they are used interchangeably, right? Divided by probability of B. Now, this is obviously very asymmetrical. Numerator is symmetrical because A and B is the same as B and A, so we can swap them. But denominator is not, because this is not, right? So it is specifically given B. So we divide by P of B, not P of A. And that's it. That's the definition, right? But there's a bit more to it, all right? What does it mean intuitively when we say P of A given B? And the idea is that when we say this, this is the mathematical description. But in real life, what we mean is B has already happened, right? B is a fact. Given B means B is a fact, right? Already happened. Depending on what context you get into, then you choose one. So B is a fact. B already happened, right? And has no probability. Right? That means it has already happened. And so the probability, if you insist, is 1. All right, something not very interesting. But essentially, we say there is no probability, right? So because something has already happened, is factual, has no probability, and let me just emphasize the same thing but slightly different perspective is that it is historical, right? Fact, happened, historical, no probability. They are all kind of saying the same thing but slightly different angles, right? So why do we then say P of V? Well, this is in this situation, in the left-hand side situation. Suppose B has happened. B has already happened. The chance of A happening, given that, knowing that, right, observing that B has happened, is this number. Whereas P of B is another statement. Right? P of B is another situation. P of B is saying, under the universal set, what's the chance that B happens? Okay, so that's the idea. Now, how do I convert this back to the counting method? The counting method, if we apply it to the numerator, is P of A intersect B, or rather, sorry, count of A intersect B divided by count of the universal set, right? Because I'm just looking at A intersect B as another set, another D set, right? So count of that versus count of, or divided by count of B over count of U. Now, as you can see, these two cancel out, resulting in count of A intersect B over count of B. So that's nice because in our example here, we can now say, oh, P of B, right, is first of all 6 over 20, and let me just clear this up. I wanted to say P of A given B, right? So P of A given B is something that we normally need to manipulate using probabilities, right? And dividing by probabilities. This is easy for mathematicians to write. But when you divide by probability, I don't know about you, I have headache thinking of what it means by a probability divided by a probability. Like the chance of A and B, 0.5. The chance of B, 0.7. So divide. What does that mean? Divide. Like, is that percentage of a divide? Percentage divide by percentage, right? To give you another percentage. What does that mean, right? In reality, it's just a bit hard to imagine. But when I do count over count, it's very easy. Count of the A intersection of B, that's 2. Count of B, not you, but count of B is 2 plus 4, 6. Right? So that's 1/3. And I can get this number very quickly and easily. And I can verify, right? I can check again, no problem. The only thing is sometimes people can using separate experiments or done by different team of scientists or done by another company or done by another researcher, done by statisticians way back decades ago or whatever it is, right? So they are numbers obtained at different time and place. And then we have no choice because we only get the probability. We don't get the count. We don't get the universal picture. So what can we do? Then we can use with we can live with the probability over probability, right? But anytime I can count, I would rather count. It's easier. What that means is also that in software, in computing world, we can count, right? We can count rather easily. Then we do the counting, right? And rather not try to operate on probability divided by probability, that kind of idea. All right. Okay. So so we have A given B like this. Okay. What does that mean in practice? So it's something like, what's the chance that it will rain? If I just ask you like this, then you might just think back. Well, okay, let's say Singapore. What's the chance that it will rain? Well, 50% chance. Singapore is like, half the time it's raining, half the time it's very hot. So 50%. If I just ask you, so you say in general. But if I say, you know what? That means today there's half a chance of raining. Yeah, because that's the answer, right? So that means every day there'll be half a chance, 50% chance of raining. But you observe that when you woke up this morning, the sky is dark, gloomy, everywhere is dark, even though it's supposed to be morning, 8 a.m. What does that mean? Likely to rain soon, right? Okay, so what's the chance of raining given that you observe the sky is dark? Now, you're not going to say 50%. You shouldn't, right? You are likely to say higher. Except when I did this experiment with my class, different people will say, okay, somebody will say 90%, 99.999%, somebody will say that. Another naughtier student, 51% chance of, okay, fine. Whatever it is, they revise their probabilities, right? Because of this, given that I tell you more facts, I give you more information, you change your perspective of what is the likelihood for A happening. You get that? Yeah. So without seeing the dark clouds, you still maintain. What should I change? We know for sure that in all the past years, about 180 days will be raining, 180 days not raining, right? So you have no reason to change. But you have more facts, more input, more observations, more historical data. Not way back, but dark clouds have gathered since 4 a.m. in the morning, right? So historical. So given this information, B, what do you think the chance of A happens? Right? A hasn't happened. If A has happened in this context here, the given B context here, if A has happened, then it's 1, right? Then or if A is knowingly impossible to happen, then it will be 0. Then there's nothing to talk about. The interesting area in probability is always between 0 to 1. Right? So if it is 0 or it is 1, I would just say there's no probability. Right? Some books will say no probability. More because the probability is very trivial, uninteresting, right? Factual or impossibility, then nothing to discuss, right? So yeah, so that's it. But here we have this description. So let me give you an example, right? Further examples. Suppose I have a tabulation. We call this the contingency table. So we have a contingency table, right? And I have 10 some values, and these values need not be ordered in any form. So in other words, it can even be a categorical table. Okay, so I have an x equal to 10. And suppose the squares, the number of squares, right, is 1 unit. So that means there's 1 unit of 10, 20 units of 1 unit of 20, 1 unit of x equals to 30. Just ignore the bottom first. Okay. So if that's the case, then let me just emphasize the x part. Okay, so just focus on the top layer because I intend to use the bottom layer for another illustration. So just focus on this for the moment if you can, right? So one such box is 1 unit, 1 count, 1 observation. Then the probability of x equals to 10, 1 unit, right? X equals to 20, 1 unit. X equals to 30, 1 unit. And we can say something like, in a one-dimensional sense, P of x equal to 10, right? First of all, P of x equal to 10 is 1 out of 3. Right? P of x equal to 10, given that x is less than equal to 20. What do you think? Well, we want to count the event that x equals to 10. That's not enough because we want x equal to 10 and x less than equal to 20, right? So x is equal to 10 and with x equals to 20, less than equal to 20. So that is to say x equals to 10. Can you see that? That means x equals to 10 and x is less than equal to 20. But 10 is less than equal to 20, so that fulfills the criteria. So the intersection is x equals to 10. So that means I count the number of squares for x equals to 10, that's 1. Right? Divide by the count of this part, x less than equal to 20. How many units? 1, 2. So 2 units. Now you see that there's a jump, there's an increase in probability, right? 0.33 to 0.5. It's like saying normally any other day in Singapore will be 50% chance of raining, but I see dark clouds. So now I've increased my probability, my perceived probability of that day will end up having heavy rain, right? So that's this kind of situation. Now, the reason why I left this bottom row not discussed is because we can also include another variable. So conditional probabilities can be one variable based, right? You just go by the segmenting, although that's not very interesting, right? But you can, right? You can. So, but oftentimes more interesting conditional probabilities especially will be found when you have two variables. Why two variables? Because these variables can take up different numbers with different frequencies. So y equals to 7 like this. So again, very quickly, we can now extend to p of x equals to 10. And I'm going to use the ampersand sign to mean and, because if I write a and d, so and y equals to 7, given that, right, y equals to 7. Let's see how we do this. So we go by count, right? Yeah, we go by count. So count of x equals to 10 and y equals to 10. Now x equals to 10 now has 2 units. But we say and y equals to 7, so there's only 1 unit, right? So 1 unit divide by p of y equals to 7. Y equals to 7 has 1 unit, 2 units, 3 units. So it's 3 units. This doesn't prove that p of x equals to 10 and y equals to 7 given y equals to 7 is equal to p of x equals to 10. The numbers coincidentally become the same but doesn't prove anything. Okay, let's try the other one because I did use the x equals to 10 and y equals to 7, given that y equals to 7. What if I say given that x equals to 10? Then the numerator is, first of all, x equal to 10 and y equals to 7 and end with, right, x equals to 10. So that's fine. That's 1. Divide by probability of x equal to 10. So that's 1 unit, 2 units. So that's 2 units, right? So again, we get different probabilities. The event that we want to have probabilities is the same. Is A, right? So this A, this is A. The B changes, however, right? The B here originally was given y equals to 7. But then in another instance, I give you different event happening. Now, event happening, you can think of it as I feed you with different information, which are facts, which are historical, which has happened, right? So if I let you know different information, you react differently because your perspective of the probability of this is different, right? Yeah. So for example, you plan to travel to Japan for your summer vacation. Okay, fine. So I hear about this plan, then I tell you, if I don't say anything, then your probability of going is never 100%. Even though you say I definitely will go, right? But it's never 100% in the probability and statistics world. So let's say it's very high, right? So I hear you plan to go there with very high chance to go to Japan for your summer vacation. You say, yeah, definitely going. So I put your probability as 0.8 and above. Okay, 0.8, 0.9, 0.8. So you say, okay, fine. Murphy's law, anything can happen. So 80% chance I'll be going. But now I feed you with information. I say, you know what? Japan has Japanese yen seems to be going stronger and stronger. In other words, Singapore dollars changing to Japan yen, we will need to pay more to get lesser Japanese yen. So what's your reaction? Then you say, well, all the more we should go, and I'm going to change now the Japanese yen. So my chance of going has now increased to 90%. Definitely you should go before the yen becomes really expensive, right? So I should change my money now, go, and then let the yen go stronger. So telling you that information increases your desire to go, so makes you all the more have higher chance to go to Japan this year during your summer vacation, right? But I say, hey, but you know what? Recently, there has been thousands of minor to middle tier kind of earthquakes being observed and experienced in the whole parts of Japan everywhere. You still want to go? A bit dangerous, Then oh, really? I didn't see that. Your friend says, okay, let me reconsider. Okay, then the chance of going to Japan reduces to maybe 55%, right? Or even lower. So you see that I feed you with different information. It will, of course, my story about this friend, all the more, stronger yen, all the more I want to go. Earthquake has happened. I might want to reconsider, right? So this is all fabricated, yes, but then it's not too far from reality. A natural person will reconsider, right? Because they are relevant, pertinent information. So this is to illustrate to you why we do these kind of calculations. The conditional probability is defined this way. Is like it's a mathematical operation, but it so closely mimic our updating of information, our absorption of new facts and observations, right? So much so that we want to change our mind. And probability now has a very numerical way to express our changing of mind, which is that we didn't change the real world events, right? Going or not going is a physical thing, right? But the chance of going, we do feel the increased urge to go, the higher likelihood of going. But how do we numerically express these numbers, right? So from 0.333 to 0.5. And that's the kind of utility, right, usefulness that probability theory allows us to or brings to us in our daily lives, in our and very importantly our decision making process. Okay, so instead of living in a Lego block world where we count the squares, clearly we can do better than that, right? We can also fill the boxes with numbers, for example. Yeah, like this. And when we do this, the numbers will allow us to represent 5 units in a single piece of cell, right? So they now become like a two-dimensional histogram. Imagine a building 10-story tall, 9-story tall, 7-story tall, 6-story, right? So going to the third dimension, this towards you, right? Towards you in the video. Then you see that if you rotate that around like a 3D model, you find that that's actually a histogram, isn't it? And indeed, it's a two-dimensional histogram. And in this case, if we ask back the same question, we say x equals to 10 and y equals to 7, given y equals to 7, what's the value? We would get 5, first of all, because x equals to 10, y equals to 7, and with y equals to 7, we still get back a numerator of 5. Right? Divided by the event of y equals to 7. Y equals to 7 means regardless of x equals to 10, 20, or 30, whatever it is, I sum across everywhere. So resulting in what we called marginal probability. Right? So this is 23. This vertical down is 13, 13, and 19. Yeah. These are called marginal probabilities because not of the literal meaning that they are marginalized in any way, but they are placed at the margins of the table. Weird, right? Just because of that. Yeah, but that's the reason why it's named. So marginal probabilities means P of y equals to 7, like that. Now, in the single variable case, like x only, where y doesn't exist, or y only, where x doesn't exist. In single variable case, we don't use the word marginal, right? And as you can see, the margin at the margin of the table makes sense only when you have contingency tables, right? So we only use the word marginal to stress the fact that, hey, you know what, even though we have two variables, for now, I like to talk about the one variable situation. So then the marginal probability of y equals to 7 is 22 over 45. Right? So if we sum up, we should get 44. So over here, we would then count y equals to 7. We don't get 45, we get 22. Are you with me? All right. Then quickly we ask again the mirror question as above. Given that x equals to 10, right, is first of all, x equals to 10 and y equals to 7, and with x equals to 10 again, so we still get back 5. Denominator, the marginal probability for x equals to 10, like that, vertically down. 30, right? We just count, that's all. Okay, next, we look at what does it mean by having independence in the events. That means two events, A and B, are independent. What does that mean? Right, so you might have seen those being set in your exercise statistics and probability exercises. And why do they have to tell you they're independent? First of all, independence. What does that mean? Let's just write down. Independent. independence of A and B. A and B are independent if we can, no, the other way around. If A and B are independent, that means I tell you, right? Somebody already ascertained that. Somebody has verified that A and B are independent. I tell you, the exercise question tells you, the exam question tells you, A and B are independent. You just assume that is true. Then what do you do? Then it is known that P of A and B is equal to P of A times P of B. So you cannot break it apart readily anytime. You need to have this condition fulfilled first, right? Then you can break apart the probabilities. So that is the reason why it is important. If you go back and look at your exercise questions and exam questions again, you see why they have to tell you that A and B are independent, or sleeping hours and GPA exam scores are independent. You sleep more, you may get high, you may get low. You sleep less, you may also get high score, you may also get low score. So they are independent. They don't affect each other. They don't influence. They don't bring up the probability. Neither does it bring down the probability. Okay. So there has been many studies. The amount of caffeine or number of coffees you drink, right, affects your health in some sense. Okay, so maybe your energy level, your recovery from sports, or whatever. So they measure, right? Number of coffees and your health, independent. Some will say otherwise, some will say they're independent. So just go ahead and drink coffee, right? Guess who sponsors the research for coffee being independent from energy level? So there can be interested parties, right? And what if it is really independent? That means you drink a lot of coffees, your health is still okay, same. You don't drink coffee, of course, your health is still the same, right? Maybe coffee has certain nutrients that are very kind of mythically, mysteriously benefiting our bodies that so far we don't know. We don't know because no scientist has taken the experiment to verify it, right? To investigate it. But that doesn't mean the effect doesn't exist, right? It will be kind of like a myth or some sort of a rumor or some sort of a unchecked truth being passed around between colleagues. Hey, you're feeling low, right? For me, I always have nine cups of coffee. That always boosts me up. Don't worry, just go ahead. See, I'm still okay. So all these small talks, casual conversations, side observations, they could review, right? Being independent or not being independent. How come you are unable to sleep again? You must have had a lot of coffee. Yeah, you know, that kind of thing. That kind of not very scientific, but you know, it has happened, right? Yeah, I've been drinking a lot of coffee. That's why I've been having a strong headache. But is it true that the coffee causes the headache? I mean, again, there's no scientific study. You didn't conduct any experiments to verify that, right? But you just make a claim like this. So again, in real life, being independent is a very hard thing to verify. A and B are independent because when you say it is independent, how long can the independence last? Let's say magically you somehow can determine that drinking coffee and health, right? You somehow can very surely say they are independent. No effect on your health. So just go ahead and drink a lot of coffee. Don't worry, something like that. Suppose you can verify that. But how long will this independence last? Are you going to say forever? I mean, you can't say forever, right? So you're going to say for next hour, for whole day, for that day alone, for the whole week, for the whole year. I mean, can't tell, right? Because you're going to, it's a semi-destructive kind of experiment, right? So by the time you determine, yeah, it is harmful to your health, then your health has gone down, right? So it's may not be recoverable. So the thing is, in real life, independence is very hard to achieve. And also another side of observation that I share with you is in real life, or maybe you should write that down. Okay, so in real life, right? Independence, complete independence, uh, independence of any two events A and B is very hard. That means kind of practically impossible, right? We can even say that practically impossible. Nothing is impossible, yes, but practically, it's like trying to say that you want to create a vacuum with your hand on Earth, right? Nothing is impossible, but just waving your hand is not going to create a pure vacuum, right? Yeah, so practically impossible to achieve. The sort of derived inference from that is that most variables, including everything like business variables, life variables, profits, number of employees, customer satisfaction, everything. Most variables are interrelated, isn't it? To some degrees, all right. Maybe the interrelatedness is 1%, 5%. Some may be 50%. Some may be 90%, right? So they are all interrelated. Like showing advertisements more makes the sales increase. Okay, so I think the recent Jurassic Park, right, movie is coming. So if they advertise more, and if you see Jurassic and the dinosaurs appearing on your screen, the mysterious uh, deep forest background scenes just somehow attracts you, right? And then you get reminded of that, and then you say, okay, I want to watch that movie to experience the entertainment. So more advertisements mean more sales of your products, of the tickets, of the whatever it is, right, that you're selling. Uh, and you're trying to increase the interdependence, right? So you're trying to make sure that the advertisement that you show will make people want to watch. So you're going to show very exciting clips, right, without ending. So you want to know the ending, come and watch the movie. Right? So yeah, you want to increase the dependence of the audience onto your product, right? So is the whole Jurassic Park series of movies, right? So when we watch one, we want to like, oh, there's a sequel to that. Yes, it must be good, right? So we want to watch, and automatically we want to watch. So in real life, we want, so long as you're in business, you want to create actually interdependence rather than independence. So that's why it is very hard to ensure that A and B are independent. Kind of ironically, in statistics, most of the theories are developed with the assumption that the participating variables or events are independent. So there you go, right? Okay, so checking that they are independent or not is kind of like a daily routine kind of event, kind of activity, right, in statistics and probability. Okay, so complete independence very hard to achieve, right? And number two, measuring, uh, ensuring, measuring and ensuring, measuring level of independence also independence also very, very difficult. Okay, all right. Now, these two are just practical observations, but what I want to show to you will be very strong and important probability derivations. And so we say that P of A given B, right, is P of A intersect B over P of B. But that just means that if A and B are independent, this is true in general, the definition, right? But I'm saying if A and B are independent, then what we relook at the formula, we see that it is P of A. Specifically, the numerator can be split, right? This is specifically allowing us to split. So we split, and then we realize, hey, we can cancel, huh? So this becomes P of A alone. Which means you can also do the same to achieve this scenario. Okay, so P of B given A is just P of B. Now let's summarize that when A and B are independent, then this is true, and P of A given B is just P of A, and P of B given A is just P of B. So all these three equations are true at the same time because they are one implying the other whenever you are told that A and B are independent. So please listen carefully again so that you can solve problems whenever the word independent is given in your exercise or exam questions, because that word bugged me and affected me a lot because I didn't know of its importance. Independent is important. It's an important word in solving probability questions. And of course, whether you are practically oriented, that means that you just want probability to help you make better decisions, fine, right? But you still need to solve it in the theoretically correct way, which is that whenever A and B are assumed to be independent, then these three equations are true simultaneously, okay? Which means you can exploit any of these three. For example, we did that here, right? The definition is evergreen. Whether A and B are independent or not, the conditional probability can be used, right? So it is evergreen. It is what I like to call the star formula, right? Golden star, but star is not enough. I want to box it up to show you that this is definition. Definition is evergreen, right? Doesn't matter whether A and B are independent or not. This is true because if A and B are not independent, then A and B, right? A and B will give rise to the probability or the count in a relevant manner that has taken into account the lack of independence between A and B. Or if A and B were independent, suppose the count of A intersect B were 10, and then now A and B are not independent anymore, so then the count could be adjusted. All right. In real life, the variables or the forces behind, the context around it, the environment, under which the variables operate will cause the A and B count to become not 10, maybe 12, or maybe 7, right? Changed. Okay, so if it is not independent. So you can see then that this is really universal. Theoretically, that means based on formulas and algebra, right? If we were told by exercise questions and exam questions that A and B are independent, then we can additionally exploit these equations, cancel, right, and then do our calculations, because things will simplify, cancel, whatnot, to give rise to a more corrected result. Okay. Now, a few points I want to make. Number one, I just shared with you, right, that in real life, it is very hard for A and B, any A and B, anything, business productivity with number of employees, business sales with number of employees, number of people in the management, and number of supervisors. Very hard to say they are totally independent. Just change, like just have 5 CEOs in our companies and 1 worker. You know what I'm trying to say, right? By design, it's already 1 CEO and many workers. So there will be always more workers than number of people in the top management, right? So they are not independent. So how can we then ever get this in real life? Because in real life, we are not solving exercises nor exam problems. We are giving ourselves situations to solve, right? So we are like our own examiner, or we need to make a decision. So how should we do? Well, if A and B, you can always assert or assume first, right? Suppose these 2 variables are independent. Suppose workers' productivities and a number of overtime days worked in a week. Suppose these 2 measurements are independent. Okay, then we go on and calculate the probabilities and then reach certain conclusions, and then see if that invalidates other observations or disagrees with other measures. Then if they disagree, then something is wrong, right? And we can come back to this initial assumption that maybe they're not really independent, right? And if they are mildly independent, like maybe 2%, 1%, then fine. Yeah, the results should agree. The fact that the productivity and number of days working overtime in a week, they are independent. So that's the thing that we want. But of course, we also covered hypothesis test for independence. And so you could look at the chi-square independence test between 2 random variables. In the video, I discuss more details about those, because here, these are point forms. That means the numbers may match, right, at a particular point, but that doesn't mean that going forward, the statistical noise and some fluctuations, some variability wouldn't invalidate this, right? And if it invalidates this because of noise, it's just mild deviation. So, example, if you check left side is 0.7, right side is 0.6995, would you say they are therefore not independent? So close, right? And if you say, yeah, because the numbers don't agree, how about 0.6999? Right? So it could be due to rounding. Your calculator has limited space, right? So maybe they are actually independent. They are actually exactly equal. So that's the challenge. So the chi-square independence test will take into account those fluctuations. Okay. Next point I like to discuss is the one-way ticket nature of this statement here. So I said if A and B are independent, right? So this means that the following 3 equations are valid. But it's not the other way around. That if you find directly, you measure probability of A and B, and you find probability of A, and you find probability of B, and you multiply them. One is 0.7, the other one is 0.5, which doesn't satisfy the equation, right? Then it doesn't prove or show anything about whether A and B are independent. It doesn't go the other way around. So it is a one-way ticket. Now, that is true theoretically. However, in practice, independence between A and B, 2 variables, is very nebulous, very hard to see or even measure. Give me a device. Show me a device, a ruler, a laser machine or whatever that indicates whether it is by meter, LED, or digital display, that A and B are independent. There's none. You just cannot have such an instrument, right? So you can only sample and then do some chi-square test and do that. But how to see that A and B are independent, right? You cannot. So that's why even if the two numbers, two probabilities on the left and right, they are equal, like this or this or this, that's not any indication that A and B are independent. And even if they are, even if you can prove it, which you cannot, but even if you can, how long lasting will that be? Because your data, they are all in the past, right? So will this independence carry on forward to the next hour, next day, next week, next year? Can't tell, right? You also cannot prove. So that's why it is filled with a lot of difficult issues and challenges, right? That's why when you do solve problems in exercises, exams, we just see this word conveniently, right? It's given to us. A and B are independent. But I just like you to appreciate that in real life, when you apply this concept in real life, there is a bit more to it. You just want to note all these points that I'm talking about. Right? And in real life, physical independence. So this is statistical, right? This is a statistical independence, right? So in real life, physical independence implies physical independence means air gap, implies statistical independence. That means if you have air gap, then this will be automatically true. When you have air gap or information gap, all right, so there is a total disconnection from the internet and the real world. You're living in a space capsule, right? In Amazon forest. Okay, so no 4G, no Wi-Fi, nothing, and you decide, right? So and you decide to do various things. Then your actions are all independent from the rest of the variables in the world, because if you become more productive, right? You just become more productive. It's not because you are given more salary, more friends, more entertainment, more caffeine, more whatever. Nothing. You're totally, isolated from the world. So air gap and in many ways information gap will lead to will enhance, right, the assumption of independence. Statistical independence. That means the three equations will be true. And of course, you see that I put a arrow, one-way ticket also, one-way arrow, because statistical independence is a theoretical result, right? So it means we can use these three equations any way we like if we have physical independence. So that means if we ensure that the accused, say in the courtroom case, right, accused and the victim and the plaintiff, right? And the plaintiff, they have no communication access to each other, then the outcomes will be independent, right? And we want that, right? In real life, we want to maintain that independence of the statements coming from the plaintiff and the victim, right? The plaintiff will say, the victim caused me this damage and that harm. The victim will say, no, plaintiff is just, uttering nonsense. I never did this, never did that, right? So, but maybe the victim say, the victim says, or the other way around, the victim is the plaintiff, right? The accused says, yeah, I did it. Interestingly, saying something disadvantages to himself, right? Yeah, I did it, right, in court. Well, if it is shown that there is lack of physical independence, right, then uh, there's there's no immediate implication that there must be statistical lack of statistical independence. But then now we start to worry, right? Because there's no air gap, so the the suspicion that the accused might have been incentivized to just admit it, might have been, threatened to admit it, whatever it is, right? So we just, or rather, the court will start to suspect, right? Or the lawyers will start to say, hey, you're not admitting this willingly, right? So the lack of independence. So that's the physical independence. But of course, we are not dealing with that. We are saying if there is information gap, if there is physical gap, right? That's physical independence. Then we can assume very safely that the statistical independence equations will be upheld, but not the other way around. Huh? If you prove that the numbers agree, I can only say that the numbers coincidentally agree, or they don't imply backwards that you have physical independence. Cannot be. Okay. All right. So that's our discussion on independence. Next, I want to bring up the discussion on Bayes' theorem. And that's the same Bayes that I opened today's video session with, right? The Bayes that allow us to update our subjective guesstimation probabilities. Let me just use that word, right? Guesstimation, our subjective estimation of chances, right? Without collection of data. That means we don't need data analytics. We don't need to gather a lot of measurements to so-called prove our case or calculate our probability. We just shoot up with a number. And under Bayesian theory perspective of looking at probabilities, that's somewhat okay, or that's somewhat okay, right? And that's nice because that we do have a lot of cases like that, right? When you say, I think I have 70% chance of passing an exam, the statistics exam, right? What do you mean? Have you done this 100 times, out of which 70 times you pass the exam? I'm sure you haven't even dreamt about taking the same exam 100 times. Much less to say you physically had done that 100 times, right or not? That's why the frequentist view of probability is also little bit problematic, don't you think? Yeah, because we hardly have not just the luxury of doing it, but the possibility of doing so. It's just impossible to say that we have done this same exam 100 times, out of which 70 times I passed. That's why now I say 70 out of 100, 0.7 probability of passing the exam, right? In order to strengthen my case, why I say 0.7. So from the frequentist approach, it will be very weird to give a number. And we should expect all people to say the same thing, right? Because it's just strange to have everyone say that my chance of passing is 70%. Whereas Bayes' theorem says, given that. So the starting point of thinking about Bayes' theorem is I have a prior probability, right? I have a prior probability, and in view of more information, I am now updating my probability to give what is called a posterior probability. So prior, my belief, right? My belief is expressed in terms of probability. My belief that it will rain and no rain is 50 and 50. Then I saw dark clouds, right? And what's the chance of dark cloud appearing? It should not appear every day, because if it appears every day, dark clouds appear every day, then it's like white clouds. It tells me no information, right? It tells me that it is equally possible that that day with dark clouds, a lot of dark clouds, it's like having a lot of white clouds. It will have half the chance of raining, half the chance of not raining. That's very strange, right? So it's not giving me any information. So I also need to know that dark clouds don't appear, rarely appears, but whenever they appear, they are almost always, right. There are days when dark clouds appear, and in the end there's no rain. Possible, but shouldn't happen frequently, right? So the more dark clouds appear and then there's rain, dark clouds appear and then there's rain, the more such, we don't call this correlation, but you get the idea, right? The more of such links, the better it is that dark cloud is an indicator that rain will come, right now. Yeah. So again, in probability, nothing is perfect. So we're not going to say every time dark clouds appear, rain occurs. Rain appears. Then that's like dark cloud equals to rain. So again, not interesting anymore. Now, Bayes' theorem essentially allows us to do a few things, right? So it has this idea of probability updates. So has a notion of prior probability. That means the before probability, right? Then initial belief. So this term called belief, which is also a very fuzzy notion, right, is now expressed as probability, right? So then you have posterior probability. These are just names. Updates, right? So they are updates of prior. We sometimes abbreviate prior probability as prior. The updates of prior based on new information or observation in the form of probabilities also. Okay. More importantly, the usage is that so updating probability is one. Or now my belief has changed. But then so what, right? So what? But the idea is that you can also use to reverse conditional probabilities. So in the theory, in Bayes' theorem theory, they developed, or rather the theory is supposed to be allowing us to update our prior belief, right? Due to information coming in, we update it and say that the chance of raining is higher or lower. In practice, the theory also happens to be allowing us to reverse the conditional probabilities. So in some sense, it means that, for example, P of Sk given Ij can be calculated into P of we do this way as well. Ij given Sk. So what we want is actually this, right? So what this means is that why does it matter to us? Because in real life, allows us to obtain conditional probabilities, right, that are either one, very expensive or time consuming, right? Right, or very labor intensive, or very takes a long time, takes a lot of money, takes a lot of expensive equipment and so on to obtain, or two, impossible to get. It's just physically on Earth impossible to measure directly. Remember how to measure directly a conditional probability? If we can look at this one, we go by counting, right? Or 2 here, 2 divided by 5, right? That's the probability of A or B given A, right? So we can do this kind of counting or measurements. That means we are able to measure, let's say, a patient with characteristics A and B. A can be OH, B can be having cancer, right? So a patient with characteristics A and B, two of them. That means, that patient is in the intersection of old people and having cancer, which can be young or old. Right? So that's, yeah. So you see that sometimes we can easily directly measure one conditional probability, but what we are interested really commercially is the other way around. You see the swap sk given ij, ij given sk. Okay, let's illustrate with an example. Okay, so we see that we suppose we say we want to know probability of disease given positive response from test kit. Positive response from a new test kit. So let's say a pharmaceutical company has created a new COVID-19 test kit, right? Uh, it promises to show, to show positive line if there is disease. But being so new and the disease, right, COVID-19 is so new also, how do we know, right? So how do we know that this probability is high? We want this to be high, right? Because if the line shows red, positive response from the test kit, then 99% you have the disease, you have the COVID-19, you have the HIV, you have the whatever, right? The disease. We want this to be high, but is it high? So how do we calculate? Well, you better find people with the disease and people with positive response, divide by total number of people with positive response. But that's rather difficult. Huh? So we'll say that this is hard. So hard to measure directly, right? But we can measure a few things. We do easier work, but do a few more work, right? So we find the probability of positive response given people with disease. So we go and gather people who have been confirmed to have COVID-19, right? To have HIV, not because the symptoms are there already, right? So doctors' diagnostics, you don't need test kit anymore, right? Diagnostics, blood analysis, and all these expensive, time-consuming, very personal, and of course, delivering bad news kind of final confirmation had been done. So we know people have disease. Then we go and use the new test kit to test on them. Then we do the count, and we can do that, right? So we can do this, and we can do this from known cases. Okay. Then we can, of course, also obtain the number of positive responses from no disease people, either general public or else other patients So long as they don't have the disease, right? Healthy people, right? Then we can do the test from healthy people. Okay. That means we want to know that given to healthy people, the test kit, does it show positive or not? It shouldn't, right? But there may be error. There may be what we call the false positive response. And we like to measure that, right? So this is the false positive. Huh? If we know the person has no disease, we know already. Given that the person has no disease, remember this is a fact. Huh? The person has no disease. We test, and out of 1,000, maybe five, maybe 500, right? So the false positive hopefully is low, but we don't know until we count and measure. So we can do that with a bit of pain in terms of time, but at least it's doable, right? Yeah, we can do that. And we also want to know the probability of disease. This is from a public health study or epidemiological studies, right, to see how widespread is the disease. So COVID-19 appears to be very widespread because widespread means more people will end up getting disease. More people will end up getting disease. So that no disease case is fewer and your false positive may end up being 1 out of 10 people, right? So 1 out of 10 people is like alarmingly large, right? 10% of false positives. But then that's more because fewer healthy people are left. So we like to know this. And once you know this, you also know of the probability of having no disease, right? So because it's just 1 minus, right? So you can then do the sum here. No disease is 1 minus P of disease. And of course, if it's not disease, no disease, but rather no disease, mild disease, disease, right? So if you have 3 bins, 3 labels, then you need to measure 2, right? Either disease, no disease, then you can deduce the mild disease or whatever it is, right? So here we have only 2 cases, then no disease is simply 1 minus disease. So once you have these, then what happens? We can then use the Bayes theorem. By Bayes theorem, right? So P of disease, P of disease given positive response is equal to P of positive response given disease times P of disease, right, over P of positive response. Now, P of positive response is nowhere to be found here, but we can easily, using Bayes theorem, of course, to calculate this by using P of positive response is equal to P of positive response given disease times P of disease. It's like the numerator here, right? Plus P of positive response given no disease times P of no disease. So now you see these components come in, right? No disease, positive response given no disease. They come in here to provide this summation for the P of positive response. Like this. So that provides for the denominator, and everything else is clear. So if you agree with me that these P of positive response, that means we give test kit to known disease people, we give test kits to known to be healthy people, we obtain probability of having disease a random person in the public having disease from health studies that should be of concern to the nation and authority. So the pharmaceutical company probably doesn't have to do it. But even if doing it themselves, it's also not going to be difficult, right? You just randomly take people from everywhere, streets, right? Or even combining with website and with some coupon voucher returns, right? As incentives, right? Then you can get an approximation of this, and then 1 minus. So then you can obtain easily. Now we get the reverse, right? Because on the right side, everything is P of positive response given disease or no disease. Everything on the right side. Everything on the left side, this term here is what we want. When the test kit shows positive, what's the probability that that person actually has disease? So I'm going to give you a table, what you call the table approach, the tableau approach, to illustrate how we can obtain the posterior probability. So this part is the posterior probability. So this is our posterior. Okay, and this is the prior. Okay, let's see. Let's call this disease, no disease, S1, S2. Okay, so disease, no disease, S1, S2. Just going to give a simple number, 0.7, 0.3. Now, it has to add up to 1, right? Yeah, because it has to be basically the person is either having the disease or not. So we have the P of ij given sk here. Then we have the P of ij times sk. And finally, the P of sk given ij, which is what we want. Okay, so over here, this is I1 is positive response, okay, negative response. Positive response, okay. So let me just draw out the table lines. Should be here. And oops, I should include the prior. And this is our posterior on the right side. So we can like move from left to right. This is our prior. Right, so epidemiological study shows people with disease, 70% people get infected. Then we have our calculation of the conditional probabilities that are easy or cheap to obtain. That means given the disease, so given the disease, given no disease, right, the chance of the test kit showing positive, right, will be respectively these things. So let's say this is 0.8 and 0.4. And of course, if you have one probability known out of a binary state, the test kit either shows positive response or not. Right? So if it shows no response, that means it's negative response. But of course, if the test kit has other gradations, right? So very strong, right? Red line, mild orange line, no reaction. Okay, then you have 3 columns here, right? For now, we have only 2 columns, right? So once we have 2 columns, it's just like the same case here. If we only have 2 labels, right? The disease, no disease. So then we can do a 1 minus to say that the no response probability, given that there is disease, that means 20% of those with disease, we knew that these patients have disease. We give them. I know 80% the test kits show positive. Of course, then the remaining has to be 20%, right? So same thing here, we get 0.6. Are you with me? Right? So like this, then we know that this is a sort of a more like a horizontally, they have to add up to 1. Yeah. And another point you might have already suspected now is that, oh, is it possible that we have disease, no disease, but test kit we have 5 gradations? Can. Definitely can, right? So it's a rectangle, not necessarily a square. But I don't want to make this a very extensive drawing work, right? So I'm just living with 2 and 2. So, but there's there's no condition, there's no requirement, there's no criteria that your test kit must always show 2, because we categorize people into two categories: disease, no disease. Okay. Okay. So then what happens in this middle section, which is another replication of this this table here? If there are 5 columns and 2 rows, then this will be 5 columns, 2 rows, 5 columns, 2 rows. So you're like having 3 tables here. The middle part here is as you see, I wrote times, which means the probabilities should times together, times the SK here. So if I do a quick mental calculation, 0.7 times 0.8, 0.7 times 0.2, 0.3 times 0.4, and 0.3 times 0.6, right? 0.18. Yeah. Then what is needed is the P of ij, right? So the P of ij, I need to carve out a spot here, literally, right, with hands and tools. Carve out a spot here. Is the vertical sum, right? So it's the vertical sum, directly adding them up. So I would get 0.68. Yeah, and 0.32, like this, just vertically adding up. Right. And on the final panel here is where we actually obtain our results, which is, let me just give you the numbers first. Okay, so it's 0.8235, 0.4375, 0.1765, 0.5625. Now, of course, it starts to look a little bit mysterious, what I'm trying to do. But let me explain. All right, so here you have the prior, right? So the prior, if I may use this as number 1 here, number 2 here, right? So this number is 1 times 2. Okay, so this number here is 1 times 2. Right, so number 1, this position times this position. So let's call this position A. So A, B, C, and D. Okay, so you can see that they are differently labeled. And this position is going to be A plus C. Let's call it E. So this is E here. And I call this F. Similarly, this position is B plus D. Okay. So B plus D equals to F. Okay, so you do a times to give this, then you do a plus to give vertically down, then of course you do a divide, right? So is going to be this is going to be uh, the same position of the cell in the middle table, right? So A divided by E, right? So A divided by E is going to be our W. So this is W, X, Y, and Z, right? So W is going to be A over E, right? Then, of course, this B over its own column sum, right, is going to be B over F is going to be X, yeah? And this guy over here is going to be C over E, is our Y here, and our final value, which is D over F. So you can see that it's non-ambiguous, the same position, same corresponding position divided by its own column total. So it will be D over F. That's our set. Okay, what we are doing here is exactly Bayes' theorem. It's not a derived version, whatever it is. We're just showing the entire computation of Bayes' theorem on a 2 by 2 table. That's all. This is called the tableau approach, right? The table approach. We are calculating Bayes' theorem by laying out all the numbers. But also, all these numbers have some meanings, right? Have some meanings. The prior, right? Then the posterior, right? We better call this the posterior. Very, very important because this is what we are after. Posterior, the updated probabilities, right? The posterior. Now, so what do they mean here? It means that, for example, given ij, right? Ij is positive, negative. Given positive response from the test kit, what's the chance that P of S1? What's the chance that the patient has disease? 82.35%. Not bad. Okay. But I think this number is perhaps a bit of a deserving of a bit of a highlight. Why? Because it's pretty large, right? Yeah. So for test kit, I would expect the main diagonal to be strong, very high, hopefully 0.99, right? And the off diagonals to be nearly zero. Also, the off diagonal here, right, is saying something like the chance, the probability of person having disease, given that the test kit shows negative response, right? So the test kit test no response, right? Yet the patient is calculated to have 43.75% chance of having a disease. So don't feel too lucky if this new test kit, right, gives you a false negative response. It shows that you have no disease, but doesn't prove that you have no disease. Doesn't verify that you have no disease, right? So this is bad. That means the test kit is not good enough, even though the positively correct, the true positive response is okay, acceptable, right? Maybe 80% and above. But the off diagonal should be near zero, right? So at least this is telling us maybe this test kit needs further improvement. Of course, I started off with just numbers that I conveniently take from the various digits to show the difference. I don't want everything to be 0.5, 0.5, then nothing is going to change too much. But at the end, if this number is to be seriously interpreted, it will be the false negative response. And it is no good, right? Too high. So we want this to be lower. Okay, whatever it is, you get the fact that this is false positive, false negative for a new test kit, right? For a new disease, and basically even for existing disease and existing test kit, is just hard to measure. Okay, hard to measure. You have to test already, wait for the patient to show signs, symptoms. And if the disease is kind of like having varying time to show symptoms, it can be 2 weeks, it can be 2 months. Wow, then very hard to complete your study in time, right? For another iteration of the test kit. That means you can't tell if your current version of test kit is good or bad until 2 months, maybe even 5 months, 6 months later, right? Some diseases are long evolving, so they take long time to show. Cancer, for example. So if you just replace everything that I've said, right, the word disease changed to cancer. Now you see that some, well, in this case, a new treatment, right? It can be instead of radiotherapy, microwave therapy. You cook the cancer away, right? So microwave therapy, a new, new instrument, new technology plus medical procedure, right? So this is not a test kit, but a new procedure. So we want to know if this, given this new, a patient given this new procedure, right? What's the chance of recovery, right? So what's the chance of cancer? Right. So if we say recovery, then this chance should be high, right? But this will take time because, like radiotherapy, radioactive therapy, drugs or whatnot, right? And cancer itself is trying to grow, and your drug is trying to suppress it. So there's a fight inside the patient's body. So it may take time to see who wins the battle, and is it a tentative win? Right. So if you measure the blood cancer cell counts, it may be reducing, but is it lasting? Is it progressively reducing? Or is it because of that procedure, that drug, that therapy, the cancer momentarily is being reduced, and then after that it overcomes and then back to growing stage again, right? So it all takes time, even if you have the money. So maybe it's easier to do the reverse probability. It's going to need more information, but each of which is either easy to do, cheap to do, right, or else at least possible to do. And sometimes it is impossible to do. So then we gather this. If you just follow the same repetition or use the tableau approach, you will end up getting the posterior probability, which is exactly what we are after. Given, right, the new cancer treating method procedure, what's the chance of good recovery for the patient, right? So whatever is considered medically good will be used as the criteria here. So that's why Bayes' theorem allows us this huge advantage in practice, which is to obtain probabilities that are otherwise impossible, right, to get. Or if it is possible, it is very expensive, and it might as well be for us to do several cheaper conditional probability measurements and then combine them. But how to combine them? And that's exactly Bayes' theorem. Okay, so I've already illustrated the structure of Bayes' theorem and its function, essentially to reverse conditional probabilities, and its main utility to us, right, in our lives, in our businesses, in our daily use, in our society, right? Basically to, help us get the kind of conditional probabilities that are helpful to us to make decisions. Should we carry forward to do the next iteration of this potentially promising test procedure, cancer treating procedure, drug development, whatever it is, right? And or not, right? So we need to make a decision. And then of course we need to label it how effective. The chance of recovery is 99.5%. Where do people get those numbers? You couldn't have done a lot of direct measurements, right? Because you have to wait for the outcomes. Because when you say the patient is clear of the disease, how do you know? right? You got to wait, right, until the sufficient time has lapsed and the patient doesn't get any relapses, and then you can at least confidently say there's no more disease. So you have to wait and wait and wait. It's a waiting, time-consuming game, right? Very expensive in terms of financing, and also in terms of the time to save more people. Because while you wait, more people would have perished because of the disease, right? So you just change the disease to any bad things, and the test kit to any detector would do. And that would have a wide applications. Okay, so for the remaining few minutes, I would like to just list without much elaborations, if I can hold on to myself, because I tend to like to elaborate uh, some of the details. But I'm going to give myself a very small space here, okay, to uh, just list out a few more potential applications. Okay, so hopefully that would convince you of its wide applicability. So example, um, auto spam detector. Okay, so suppose we like to do this, and of course it can be any other detector, and it also can be any other form of documents, right, or channels, or YouTube, right, or movies, videos. It doesn't have to be email. So it can be like um, obscene scene detector, right, for video processing. So that's also possible. Okay, so what do? We want to know the chance that this email is a spam whenever we detect the word violent, right? Violent and the word free. Okay, so this combination, that means inside an email, there are uses of the words violent and free. When we see these two words, however many times for now, maybe more violent, more free, whatever. But so long as these two words occur in any incoming email, do we consider that a spam? If it is a spam, then we put it in the junk box, as you probably know, right? If it is not, then we leave it in the inbox. So the your email software is doing decision making, and it needs to know this probability. But how to measure this conditional probability directly? You think about it, right? Also a little bit challenging. But we can get. So this is hard. Or if you can get, it is likely a direct measure of it is likely to be unreliable. So, but we can get probability of violent and free, right? Given spam. So we look at all the past spam emails. We look at in the junk box, right? How many of such past emails, because they are past emails, so they are very verifiable. You can inspect, search for the words, right? And how many of such emails in the past contain violent and free together? So then you can also look for violent and free. So now the criteria is both words must occur in your normal inbox. in the past mails that are not considered spam, how many of those occurred? But eventually you pull them out from the junk box. You look at it and say your friend sent you a political review of US free speech, right? Whatever it is. Right? So of course there will be some mentions of violence and free and whatnot, right? Violent demonstration and all that. And then it was put in the junk box, but later on you say, hey, I haven't received it. Oh, I've sent it. Maybe you check your junk box and then you say, okay, fine, I need this. So you pull it out and not classify it as spam. And you can do that, right? So how many times did such emails occur? Right? So you can do that easily. And of course, we can calculate the number of really junk emails in your junk box divide by total number of incoming emails. That will be the percentage of spam. And of course, we can then calculate the percentage of the chance of not spamming of an email that is not spamming. And we can then use Bayes' theorem to calculate the probability of spamming given. So here comes an incoming email. It contains the words violence and free. So the software now needs to calculate, is this going to be higher than, let's say, a cutoff, a 60% cutoff, right? So how do we calculate this? Well, you can do this as P of violence. I did say violent. Violent and free, right? Given that it is a spam times probability that it is a spam, that's why we need this probability, divided by P of violent and free, right? And this we can obtain from P of violent and free given spam times P of spam, like the numerator, plus P of course, violent and free given no spam times P of no spam, not a spam, right? And when you do this, then of course we are doing this one. This looks like a huge formula, more because of the violent and free, right? Yeah. Or in future, if we want to have violent or free, yeah, then or violent or demonstration, like violent or gunshot or demonstration. You can expand. So it does seem like more and more complicated if you write them out, but actually the idea is very simple. It's just following the same. You can see the repeated formula being used. Where's my formula? Yeah, over here, right? Yeah. So the repeated formula is actually exactly the same if you replace the words, the brackets, the calculations. So there is a multiplication, there's an addition, there's a division, right? Yeah. So there is a multiplication, there's an addition, then there's a division as a final same. Okay, good. So and of course, this is a sort of an example that you want to detect problem, to change the word spam to problem, given certain manifest signs or indications or information, right? So I've received this information. How can I conclude whether this is a bad guy or not? So same thing. Okay, and let's just round up our final thoughts, right? Let me share with you. Three more examples, right? So Other examples, very, very broad category, huh? Just to uh, inspire your thoughts and see if you can think of even more examples. Number one, financial accounting, insurance fraud, fraud detection. So fraud detection is a bad thing, right? Bad guy. Huh? So instead of detecting spam mails, which is important for our daily use, we can also apply it to industry, right? So are there bad cases? Yeah. So we want, in these cases, we want to know the probability of a fraud occurring given transactions, right? Given whatever transaction measures that we can measure, which we can capture. So, for example, in financial transaction, it may be the timing of the transaction, movement of the cash flow, the amount involved, the destinations, who is the paying party and receiving party, and all those capturing data. For accounting, you don't have those, or not directly equivalently. You can still have those, but you can also say how often, right? How often are foreign exchange currencies being used as receiving as revenue? What about our accounts payable, accounts receivable, our balance sheet, our assets, our so accounting you can detect any abnormality that is peculiar to this company, or this industry. And for insurance, detecting fraudulent claims, whether it's car insurance, right? Uh, you know, uh, colluding with the car repair service workshops, doing overclaim, inflated claims, right? Cheating the insurance companies. So all these fraudulent activities, or else medical fraudulence, right? So colluding with the doctor to inflate the claim, or maybe the patient is ignorant, but the doctor inflated the claims, right? So there are cases, right, happening like that. So insurance will have a need to want to clamp down on these fraudulent cases so as to be fair to other uh, premium paying customers who are not performing fraudulent claims, right? So because when premium increases, that means the good guys are subsidizing the bad guys to get their undeserving uh, insurance compensation, which is not actually compensation, right? So they are just cheating. So that's why you want to do this one. Right. So again, we use we can say can find P of transaction given fraud. So we knew that the fraud had happened. So we find those transaction patterns, right? We find P of fraud. We find P of transaction patterns. So basically trying to say that we can do these, right, in order to do what is very hard to find. So number two, we can talk about ad clicking, right? Conversion. Okay. So what we are trying to do is to say that we want to find P of, if you click an ad, if you click on it, what's the chance that you will buy? Of course, we want it to be high, right? So if we are the advertiser, it may be that our content is not good. So if the conversion rate is low, people see our advertisement, maybe it's a movie, maybe it's a you know short clips or whatever, or narration, right? Our content is not good enough. The rate conversion rate is low. So we're using this as the future conversion rate. The probability is low means the future conversion rate is low. So we better change our advertisement. Um, there's once I saw an advertisement. Um, it's a local advertisement, something like some sort of services or what. So it goes something like this guy saying, you know what, this it's work. So they're selling a service, and then the guy came up in the advertisement proclaiming that it's work. Wrong pronunciation, but it was recorded and played. It's work. And then end. Probably they detected that the buying rate was very low, so they revisited, and then later on, I saw the same company showing similar ad but updated. It's work, right? And they change it to it works. Can you hear the difference? Earlier version, it's work. You're like, it is work. Using our services is like work to you. Who would want to buy these kind of services, right? Later on, the version was, it works, which is what we often hear, right? It just works, right? It works. And then many years later, I think it's another toothpaste company having this lady scientist coming up saying that this toothpaste is going to be very helpful to sensitive teeth, right? You probably know what I'm talking about. And the lady scientist just walked. It works. And the pronunciation was crystal clear to make sure that it was said as it works, not it's work. Right. So all these nuances, well, sorry, just trying to show you that sometimes you don't plan to have a bad video, right? But good or bad video, you won't know until you air it. I'm sure both parties would have done a lot of verification and check and check before they air it, because it's expensive to pay for a video ad. But despite that, mistakes do come up, right? And sometimes it's just cultural mismatch. So the content is very good, but shown and there's no buy, right? So we want to do this, and it is going to be super costly to try it out to see, then check, correlate with the buying, either number of times or amount, and then say that it's high or low, right? So it's expensive. So what we can do, however, is now you can probably even anticipate what I'm going to write. We can do the probability of ad click amongst those who have earlier bought, right? The chance of buying in general, how many people buy after browsing, and the probability of ad click, which we can get right from either estimation or the analytics from Google Ads and all that advertisement platforms they will provide, right? So number 3, and that's going to be our last example. I'm trying to give you like different aspects, not in the same industry, not in the same functional use and all that. So last one is not last one, but last on my list here is the product defect source tracing. Right? So product defect in manufacturing is a very common activity. Not that you want to purposely manufacture defective products, but everybody in the manufacturing industry knows that Murphy's Law, right? You of millions and millions of Coca-Cola bottles being produced, some, hopefully very few, will be, having leaky cap, having a deformed bottle that doesn't look nice. Otherwise, it's drinkable, but then it doesn't look nice. It's like Coca-Cola selling odd shaped bottle. Hey, how come they are having such poor quality control, right? So we always want to check for defects, but sometimes the defects come from uh, ourselves, inside our factory, inside our equipment. Those we can check. The supervisor will have all the details. But if we are already having very high quality, such as Toyota, and in the complex manufacturing, sometimes you directly integrate the components from suppliers. And if supplier has defects, you will be embedding their defects into your products, which happened unfortunately to Toyota once, right? That the defective airbags, right? In the end, they were installed into Toyota cars. So everywhere, everything inside Toyota is like quality, except for the unknowing, unsuspicious airbag. Okay, so those airbags went to the roads and then actually didn't inflate, or else inflated, but pressure was too high or whatnot. So both cases, they are defects. So we want to know who caused it, right? So you like when there's accidents, maybe the airbag inflated, maybe the explosion was too powerful, right? The explosion itself caused the death, not the accident. But after the accident, after things have settled, you can't tell because the explosion was like pop like that, right? So you can't tell. And how do we trace it to which supplier was at fault? So we want to know probability of a defect based on a supplier behavior. In other words, we want to know some sort of a leading indicator before things go bad or things show up. Supplier behavior, these can be, I won't list out because it's very manufacturing oriented, but I give you some examples verbally. So these can be, for example, delivery, late delivery, the number of times deliveries were late, the rejection quantity or rejection counts, like how many pieces of the received batches were rejected, how many times of such rejection happened. Even if one item was rejected, that's considered one count. 1,000 items rejected, also one count, right? So how many times? So all these are parameters and measures that we can measure on a per supplier basis, right? So what's the probability that there is a defect when the supplier exhibits such a behavior? Oh, you are late again. That means the probability that you have defect is going to be 87%, for example, right? So of course we can guess, oh, you are late again because you are last minute patching up. Oh, we just detected before we shipped out that we have some defects. That's why we quickly rush to remove the defects and then patch up with our inventory quantities and then deliver to us here. That's why you are late. So whenever you are late, high chance that the cargo will contain some defect, something like that, right? So we can guess all we want, but better to have a probability. That's the whole idea. So this will be a leading indicator, right? Now, this will be hard to find, but we can find, right? So you can see I'm changing to green, means that it is relatively easier, cheaper, and more readily available probabilities, which include such things as supplier behavior, given that there is a defect. So defect was accidentally discovered or reported back to us by our customers. So there was already a known defect. Then you check back. Hey, at that time you were late in your delivery, right? Oh, at that time you delivered to us surprisingly high number of defective goods in our sampling checks. Or that time you actually had a sort of earlier delivery. So earlier delivery is also not a good sign. Maybe you anticipate that your site, the shipment will be late, so you sell us your previous inventory, right, which is about to expire, whatever it is. And you need to find the probability of defect, and you need to find the probability of supplier behavior. And again, as you can see the parallels by now, these are readily available, right? Or you find that they are either on your records already, or you can just do a minor processing. You can extract the information out very easily. So if they can, if the easily available or low cost yet highly reliable information can be made to combine in a way to give you a sort of not forecast but prediction. Prediction. That means it's a lead indicator of potential problem in the future. So probability is always about future. So the future chance of defect happening, a defect being found, given that the supplier is already exhibiting this behavior, is some cutoff, right? Is above some cutoff, then we better not use you anymore because high chance we cannot take that kind of chance. So this will be taking action before things happen, right or not? Yeah. So it's immensely helpful, and sort of reminded me about this lead indicator to link you back to this reversing control. And oftentimes it could also be that one is the future, one is the past. Actually, this is normally used as the past, right? So one can be the past, and when we have the other conditional probability, when we flip, it could mean the future, right? So that we can flip the time. Flipping time is physically not possible, but thanks to Bayes' theorem being so generally applicable to any events in terms of swapping the conditional probabilities, it is not going to care whether the events happen before or after. It's just events, right? In the probability, in Bayesian probability space. So we can use that to flip past events into the future and say that, hey, in future, given such lead indicator, that means they happened already, right? Will this have high or low chance of happening even more into the future, right? So that's very, very helpful in our decision making process. Okay, I hope you have gained a lot of more practical understanding and grasp of the power of Bayes' theorem after this video. And thanks for your attention. See you in the next video.